So it's called the method of undetermined coefficient. This occurs when you have second order non-homogeneous linear coefficients, linear ODE. Okay. So the solution would be the solution, the linear combination of the homogeneous solution, which is this. This one, and the particular solutions, Px. This we are able to get it, the homogeneous solution from the previous example. This one will depends on the Rx, or the function on the right side of the equation. So let me skip a little bit on this one. So if we have a constant coefficient at this form here, you have three rules regarding the solutions. First is so you want to determine your, remember, y equal to yh plus yp. You have this from the homogeneous solution. This will depend on Rx, which is this. So the rule number one is the basic rule. You just need to choose the solution based on the Rx itself. So if Rx is one of the function on this side, then it has corresponding choice of yp on this side. So if this is, for example, y double accent plus 2y accent plus 3y, for example, equal to, let's say, e to the power of 2x. So your choice of yp is equal to c e to the power of x, like this, 2x in our case. Okay, so let's try this in our example. We have this y double accent plus 3y accent plus 2.25y equal to minus 10 e to the power of minus 1.5x. So this is Rx. So this equal to Rx in form of c e to the power of gamma x. So the solution will take also this form. So that's why the solution choose yp equal to, in the beginning, okay, yp equal to c e to the power of minus 1.5x. But we have also a second rule that mentions if this has been the solution from your homogeneous solution, then you should modify this. So on our example, the first step is to find the homogeneous solution of this. So the characteristic equation is this: lambda square plus 3 lambda plus 2.25 equal to 0. When you solve it, it turns out it has double root. Lambda 1 equal to lambda 2 equal to negative 1.5. Okay, and then if that's the case, so your YH is linear combination of the solution. The long form will be YH equal to C1 e to the power of lambda 1x, which is 1.5. This is x, and plus C2 e to the power of minus 1.5x. But since it's already used over here, so you put another one x over here. So it will become this. So you have actually on our case is the homogeneous solutions like this. If we take a look on the YP again over here, they have the same, they are not linearly independent with these solutions because this has been used as this one, C1 e to the power minus 1.5x. So you put x over here, but again, it also has been used over here. So you put x squared over here. So cx squared e to the power minus 1.5x is your choice of yp, which is why it's over here. So it's called it's the second rule, also called the modification rule over here. So if a term of your choice of yp happens to be a solution of the homogeneous ODE, then multiply your choice by x or by x squared or even by x cubed if you already have the solution available. And then the third rule is the sum rule. If Rx is a function of, let's say, not PP already used, so let's say Qx or maybe Sx plus Tx, then this will have a corresponding pair on the table, and you just need to add them independently. Okay, go back to this example. Since we already have choice of yp, then we want to get what's C over here, because it's a constant that we need to determine first. So we derive to get yp accent this and yp double accent this, and then substitute all of them yp double accent and yp accent and yp double accent into the original equation to get the C value. So we have, this is y double accent comes into here, y accent comes into here, and the yp comes to the last term over here. So we have C, we have this, and we can just solve algebraically, collect the same power, same coefficient. If we do that, the coefficient of x squared will be 2.25x squared. So if you take x squared like this, it will be 2.25x minus 4.5. Oh, sorry, it's not x anymore because c, yeah, c. And minus 4.5c, and then plus 2.25c. So if you modify this, it will give you 0. So the coefficient of x is 0, and then in our case, it's equal, the coefficient of x square in on the right side is also 0. So it's 0 equal to 0, so it doesn't give you information on this. And then if you take a look on the x, coefficient of x, yeah, it's also becomes 0. Let's see if we have this. This is minus 6c, okay, and then this is also plus 6c, okay, then it's equal to 0. So it's same, 0 equal to 0, so also doesn't give you information. But if you take a look on the last term, over here you will have 2c, and then it's equal to minus 10. So you end up c equal to minus 5. So you just substitute this into here. You will have your yp is equal to minus 5x squared e to the power minus 1.5x. So your solution, general solution is y equal to yh plus yp is equal, this is yh, and this is yp. Okay, so that's how you use the, it's called the method of undetermined coefficient. We'd like to have a feedback. What do you think the drawbacks of this method or the limitation of this method? Any idea? What's the limitation of this method of undetermined coefficient? Anyone? Okay, let me Reza Putra, you can unmute yourself and then try to.
Yes, sir.
What will be your take on this? What will be the limitation of this method?
The limitation. What do you mean by limitation, sir?
Well, you can use this method easily, right? You can understand how to use this method.
Yeah.
Okay. But what's the difficulties of using this method? What will be the drawback or the limitations of this method?
I think the difficulty on this method is to define the YP, to define the YP accent and YP double accent. Because just now I wanted to ask something about the problem that you have just.
Go ahead. Do you have questions on the example?
Yeah.
Okay. What was it?
So why do we need to omit the factor of e to the power of minus 1.5x, sir?
We didn't omit them. We still use that. As you can see, it is still the solution for the homogeneous and also for the non-homogeneous solutions. So we did not omit them. So they are still there.
Okay.
Okay, Reza, how about if I ask you this? Can I use this method to find, let's say, y double accent plus 2y accent plus 6y equal to ln y, for example? Can I use this method for this?
No, sir.
Why is that?
Because the type of the equation is not included in the term in Rx.
Exactly. So the limitations for this method is if your functions only are at the one that listed on this table or the combination of it. So you can still have solutions for if Rx is equal to 2e to the power of 5x plus sinus omega x, for example. You can still do that. Sorry, this should be ln x, yeah, because this is Rx is a function of x. So that's one of the drawbacks of this method. You have to have Rx listed on the table, and then you also have to have a constant coefficient on this one. Okay, very good. So let's continue. But fortunately, this function is pretty common. The strings function number are pretty common on physical or mechanical problem, as we can see later on the next example. So this is an example of the application of the method in the spring and mass system. Okay, remember this one. But on this case, you don't have external force acting on it. That's why it's equal to 0, because sigma F equal to MA. And if you don't have any other forces acting on it, you will have this equation. But for most of the application, you have external forces. For example, for your shock breaker, you have the pump, you have the rod that going to give you reaction force of your weight, and then you have this one over here. Take example that the external force is equal to FO cosinus omega t. So that's one of the examples of having external force. So the equations model become this. This is the external force given to it. Okay. And then this has become non-homogeneous second order linear ODE. Then we can solve it according to the undetermined coefficient method also. So the solution, if you take a look on the table, if you have form of k cosinus omega t, for example, then your solution is taking this form. Let's take a look back on the table. So as you can see over here, you have k cosinus omega x, then this will be your choice of solution. So we going to implement the same method to solve this. Before that, of course, you need to find what YH first, right? You need to find YH, and then after that you find YP. So Y equal to YH plus YP. So yeah, so this is the final solutions. YH equal to Y equal to YH plus YP. There are some cases over here. You can have undamped force oscillations where your solution will somewhat form like this. So this solution, if you have the this is one of the possible solution, and then you can see this is like a superposition. So on the undamped force oscillation, the external force kind of adding to the to the initial oscillations. So usually they have the same phase, so that they will be enhancing each other. So it's kind of superposition of two harmonic oscillations. Second case, if you have the resonance, this is very interesting. So on the superposition of the two harmonic oscillations where they have a similar phase, they will somewhat forming a joining of two waves together, superposition. But there is a special case of this condition when you have the frequency of the excitation is matching input and natural frequencies. So omega is equal to omega 0, while omega 0 is a natural frequency of the system. So what in our case, the solution become, the equation become this: y double action plus omega 0 y equal to f0 over m cosinus omega 0 t. And the solution will change a little bit into this. So it's not this anymore. This is the solution if there is no resonance. If there is a resonance, it will change into this form. This one over here. And if you plot y based on or according to t, the time, you will have this form. So as you can see, as time goes by, YP become very high, very large value on this one. So on the mechanical vibration system, if you want to avoid resonance, because as you can see, if there is a resonance, then you will have this is Y grow large subsequently, and then it may break your material strength, for example, because of the displacement is more than what it can hold. So this is can be modeled into mathematical equation, and we can solve actually what will be your displacement after a given time, okay, and what will be your displacement at that point. Okay. This is if you have like force undamped oscillations when the difference of the input and natural frequency is small, then you can have this. So the Y will not be over too large. It will become smaller, but it will repeat again on that. So it's called the beats in this one. Okay, case number 2, damped force oscillations. On this case, you will the oscillation will diminish over time. And then the third, I think the one is something like this. Let's go. Okay. So and the third one, the underdamping is not on our practical interest. So we only have two conditions. First is the damped force oscillation, and then the overdamp. The damped force oscillation can have general conditions, or you can also have the resonance. In that case, on the resonant case, just the notes that you need to highlight in this one is if the omega over here is equal to the natural frequency. So if you have a system and then they give you the natural frequency, the omega 0, then you should avoid giving the same frequency into the system to avoid resonance. From the mathematical point of view, you have to avoid the excitation, which is this one. You have to avoid this one, this omega over here, at the same value of its natural frequency, which is given on the problem itself. If they are the same, then you will have the resonance on that. Okay, any question until this point? The electrical one, I don't think we can. There are no example available, but I think just to give you some knowledge, we can actually, especially for the one that interested on the control system, which has a mechatronic and so on, we have an analogy between the mechanical system and an electrical system, where the mechanical system have mass is analogy on the inductance, the damping constant is R, the spring modulus K is on the 1/, capacitance, and then the driving force is the electromotive force, the current is the displacement. So usually you want to find like on the mechanical system, you have Y double accent plus this is M, My double accent plus Cy accent plus Ky equal to 0. So on the electrical system, you usually have L, I, double accent, plus R, I accent, okay, plus C times I equal to 0. So they are analogy. So if you want to find what's the current at any given time, you're also able to utilize the method that we have discussed. Okay. So this is another method. So if the Rx is not available on the table, okay, we can still solve it using what we call the method of variation of parameter. So this is lies on the concept that the solution of your non-homogeneous actually can be formed from the solution of the homogeneous. Okay, so the method of variation of parameters, your particular solution here, over here, this one is a combination of y1 and y2, when y1 and y2 are the solution for the homogeneous. So this is a method when you don't see your Rx on the table, you can use this method of variation parameter, where you can use this formula to find your Yp. Y1 is the solution of your homogeneous and Y2 also. But now you have another variable of what we call the Wronxian. The Wronxian is formulated this. Y1 is this, again, the solution of homogeneous, and Y2 is the solution of homogeneous. So if you have known the YH equal to Y1 plus Y2, for example, then your Yp is or can be obtained using this formula. First, you need to find what your Wronxian is. And then after you find the Wronxian, you can use this formula to get, it's called also the Lagrange method. So this gives you a way to solve non-homogeneous ODE with the prior known of your homogeneous solution, but not on the table that is set for the particular solutions. And this actually not only apply to the two or the second order, but also to the higher order. Let's check this is examples of it. So here we have y double accent plus y equal to 1 over cos x. And this Rx is not listed on the table. Okay, so what we do is we try, of course, finding the homogeneous solutions. First, y double accent plus y equal to 0. Okay, and then that will be lambda square plus lambda equal to 0 plus 1, sorry, because it's the original form is y accent, so lambda square plus 1 equal to 0, so lambda equal to plus minus I. Okay, so we have a complex solution on this one. So for the complex homogeneous solution, we will have y equal to yh, yeah, equal to a sinus omega x plus b cosinus omega x. But we take this one, the omega is equal to 1 in our case. So we have the solutions of this homogeneous as cosinus x and sinus x. Okay, so we find the Wronskian of it. The Wronskian will be y1 times y2 accent, and then minus y1 accent times y2. So y1 is cosinus x, and y2 accent is cosinus x, and then minus y1 accent is minus minus, yeah. Wait, what's the wrong? Yeah, the same one. Oh, this one just a change of urutan subsequent. So it's become y2 y1 accent is the same one actually. Y2 is equal to sinus x, y1 accent is minus. So this is y1 accent is equal to minus sinus x, y2 accent equal to cosinus x. Just substitute them, and then it's turned out to be 1, you Wronskian. And then you substitute to this equation, this one, over here. So y1 before is equal to cosinus, so yp equal to negative cosinus x. Integration of the y2 is sinus x. The r value is 1 over cosinus x divided by 1, since the function is 1 dx. And then you have plus y2 is equal to sinus x. Integration of y1 is cosinus x times 1 over cosinus x divided by 1 again. This is dx. Okay, so this will cancel. So it's become x sinus x. This will become tangent x. Integration of tangent x, this will become minus cos x. Okay, so so the solution will be like this for the yp. So we have here, or we have here. So the since we have the yp over here, and then we can also have the homogeneous solutions, we join them together to have the final general solution. So C1 plus ln cos x times cos x, because the ys is equal to C1 cos x plus C2 sinus x. And this one is C2 plus x plus x sinus x. So this will be your solution for this one. And this is the case of when you don't have the damping over here, and then you have the excitation force like this. So this is actually pretty applicable on your vibration system where you don't have any damping coefficient, but you have this k value input on this equal to k over m equal to 1 on this case. And then you have the excitation that will give you the external force continuously with the 1 over cosinus x as the oscillation form. Okay, any question until this point? Okay, if not, then we can continue to let's see, do we have higher ODE? So it's good progressing, because once we know how to solve the first order, the second order, especially the second order, then you will use that concept of knowledge to solve for the higher order. And fortunately, there are going to be simple progression, or basically similar method to solve the higher order. So the higher order ODE have, of course, higher than two order of derivations. So for example, in our case, okay, like this example. So if you have the, for example, is the simplest one with the constant coefficient y triple accent plus, let's say 3y double accent plus y accent plus y, for example, equal to 0. This will be the simplest one of the higher order, because in our case you have third order and a constant coefficient, and a 0 means it's homogeneous. So that's the simplest one. But the general form is this. Okay, so this is homogeneous. So the theorem of this homogeneous linear ODE is the sum of constant multiple of solution on interval I are also the solution on I. So the linear combinations of the solutions is also the solution. So for example, if you have y8, y1 as your solution, y2 as your solution, and y3, so your homogeneous solution also a combination of this. So you have C1, Y1 plus C2, Y2 plus C3, Y3, also solutions. Okay, so it's a combination. So this one again, and this is also the same. I will skip this one. This one still skip. Oh yeah, the Wronxian. The Wronxian also extend from the second. Remember on the previous slide we have W equal to Y1, Y2 accent minus Y2, Y1 accent. That is for the actually for the Y1, Y2, and then you have Y1 accent, Y2 accent over here. And this is actually a determinant of this. So if you take a look, this one, Y1, Y2 accents minus Y2, Y1 accent is actually the determinant of this. So if you have higher order, you're going to have Y1, Y2 until Yn, and Y1 accent, Y2 accent until Yn accent, and so on. And your Wronxian is actually the determinant of it. So the simplest one, if you have 3, so you're going to have 3 solutions from the homogeneous Y1, Y2, Y3, and then you have Y1 accent, Y2 accent, sorry, Y3 accent. Over here, Y1 double accent, Y2 double accent, Y3 double accent. And then the Wronxian is actually the determinant of this. So you find the determinant of it. Okay. Don't worry, we'll use that later on. We can skip this one. Okay, now we can try to find the general solution of this. We start with the simplest one, what we call the constant coefficient homogeneous higher order ODE, just like what we write previously, y triple accent plus, let's say, 3y double accent plus 2, or plus, let's say, plus 4 y accent plus 1 y, for example, is equal to 0. That's, we can start as simplest one. And then we're going to do the same thing like what we did for the second order. We're going to develop the characteristic equation of this. So the characteristic equation of this equation, this is triple axiom, is equal to lambda cube plus 3 lambda square plus 4 lambda plus 1 equal to 0. And then the same thing like what we did for the second order, we tried to find the roots. What will be the lambda over here? What will be the lambda 1, lambda 2, and lambda 3 over here? It's basically finding the roots of this equation. You can use your programmable calculator or computer, or you can use what we call the synthetic division, if you still remember on that, of this equation. The point is to find the roots of it. And the solution is based on the roots. So the solution is this. So you have y equal to c1 e to the power of lambda 1x plus c2 e to the power of lambda 2x plus c3 e to the power of lambda 3x. If they are different, if lambda 1, for example, lambda 1 equal to lambda 2, then your solution will be y equal to c1 e to the power of lambda 1x plus c2, then you have to add x over here, e to the power of lambda 2x, which is the same as lambda 1, plus c3 e to the power of lambda 3x. So the same rule applies. They have to be linearly independent each other of the terms. Okay. Okay. No questions? Let's try this example. Okay. Solve the ODE of y minus 2y double x and minus y plus 2y equal to 0. How do you find this as the root? Well, you can use your synthetic division if I prefer to do that. So this become 1 minus 2 minus 1 and 2. Take one roots is the simplest one, is usually on the last one over here, 2. So this is become 1 times 2 become 2, and then you add become 0. 0 times 2 is 0. So this is minus 1 times 2 become minus 2 plus become 0. So you have 2 as one of the roots. And then you can go back over here. If this is minus 1, let's have that minus 1 and a 1. It's 1, so 1 drop to 1. And then you multiply this with this. So it's minus 1, and then you add them. So this is an addition. So minus 1 over here, and then minus 1 times minus 1 equal to 1, and this will become 0 too. So you have 2 minus 1, and finally this will be, if you change this one, become x minus 1 equal to 0. So lambda, I'm sorry. So lambda 3 equal to 1, lambda 2 equal to minus 1, and lambda 1 equal to 2. It's the same over here. Although they have different lambda 1, 2, and 3, but they're the same. So your solution is y equal to c1 e to the power of lambda 1, which is 2x, 2x, yeah. And then plus c2 e to the power of lambda 2x, which is minus x, plus c3 e to the power of lambda 3, which is x. So this will be your solution. But this only for homogeneous, because this is equal to 0. Or you can also use the factorization, for example. This is called the synthetic divisions, and to find the roots of them. If there is a root, they can also have a complex roots. Any questions? Okay. If you have a real double root occurs, say lambda 1, I think we did this, then you have to multiply with x. Let's do an example on this. That's we have y fifth order minus 3y for derivative plus 3 triple accent minus y double accent equal to 0. If we the characteristic equation will be like this. So if we do synthetic division, we will have 1 minus 3, the coefficient 3, 0, because you actually have y, I'm sorry, not 0. Oops. Erasers. Why is that working? Let's just get it. I cannot clear this one. Never mind. So this will become 1. And the last term will be 0 because this will be lambda over here. 5, 4, 3, 2, 1. Okay, never mind. So we have like this. So if this is 1, we can. So 0 is one of the factors, right? If you, or you can also do like simplify this first. You will have lambda square taking out, so you have lambda cubed minus 3 lambda square plus 3 lambda minus 1. So your synthetic division will be much simpler as 1 minus 3, 3, and minus 1. But remember, you have 0 as one of the roots. Okay, so and then you will have, let's say this is minus 1. It's minus 1 at the, oh, this is actually really, this is a cube equation equal to, so this is lambda squared times lambda minus 1 cube equal to 0. So you will have lambda 1 equal to lambda 2 equal to 0, and then lambda 3, lambda 4, lambda 5 equal to 1. So you will have the solutions y equal to C1 e to the power of 0 plus C2 e to the power of 0 plus C3 e to the power of 1 x plus C4 e to the power of x plus C5 e to the power of x also. But as the modification rule mentioned that we already have C1 and e to the power of 0, you have C1, so you have to put x over here. This one, then you have to put x over here. And this is since already, so you have to put x squared over here. So you will have, end up become y equal to, let's take out the, well, not, C1 plus C2x plus, to take out the e to the power of x, we can C3 plus C4x plus C5x squared as your solution. Okay, any question? Good. I don't know why I cannot delete this one. Oh, okay. If you have a complex roots, so you have this real component and a complex component, gamma and omega. So your solution will be taking this form. This is example of when we try that into the form beam, where this is the applications. So the bending moment M is proportional to this is properties related EI and the y double accent. But the y double accent here is not, it's not accelerations actually, is the deformations, the deformation of this. So we have this fourth order ODE for this case. You have a beam which has load, usually by its own weight, or also if you have like load on top of it, so you will have these deformations. If they are supported, then it will somewhat form like this. There are several kinds of support available on this one, so we're going to take a look on that one. So we have first the case of simple supported. So as you can see, this is fixed, and this is only like a pin on it, so you can actually move. So in our case, the simply supported will have the initial value condition of y equal to y double accent equal to 0 at the beginning over here, and also at x equal to L. Okay, if you have clamp on both sides, okay, then y equal to y double accent at 0 and at x equal to L. If you clamp at x equal to 0 and then free at x, so this is also called the cantilever. So you only fix it over here, but you just leave it free on the other side. You have this initial condition. So let's use the simplest. This one, y equal to 0 means no displacement, and y accent equal to 0 means there's a horizontal tangent equal to 0, and then y double accent equal to 0 means no bending moment. Y triple accent means no shear force on that. So the simplest one is you have simply supported beam, okay, with a uniform load. This case occur usually when you have no load. I mean, it's only the load is due to the mass of the beam itself. Or if you have like the uniform mass above